Today we're going to see the fundamental equations for planar motion for the velocity and acceleration of this particle that you see sliding on a rod on the picture you see on the left. So let me explain to you a little bit more on the problem here. We have this rod. This is the black line, and we have a situation where the let's see, you have, this is the rod, this black line. So this little square is a color that slides on the rod, but the rod is rotating with omega at the same time. It's rotating with omega at the same time. So just imagine if you were in this particle as if you would be infinitesimally small, and you get in there, you will see yourself going along this path while at the same time turning. So the new position is P. So the question is, what was it necessary for the particle to acquire the new position? I submit that this, in fact, is the change in the R, right? But that was due to two components of motion. One, that you could say that this is like that, is composed of two components of motion. So this would be like r dot, the change in the velocity due to the hold on for a second. I erased the one too many. So let's see. If we fix this, this is where we were, right? Yeah, let's keep it there. So what I was trying to tell you is that there is, oh no, yeah, okay, let's try that. What I was trying to tell you is that this changed because of the of this change in the r vector, but this is due to the rotation. So if this is like an arc with relationship to the, if this is like just imagine a small change, so this would be r times omega, r omega, right? Or r times d theta dt, like this. So this is due to the translation, you may say, and this other one is due to the rotation. Very good. So you see, if you have the r vector, you may say what is the change of the vector d r dt? What is this? This would be the change of the vector with respect to time So this, remember, this is a vector plus this r, which is really the perpendicular. This is perpendicular to the perpendicular. These two lines are perpendicular to each other. So you have, if you express as a cross product like r cross or omega cross r, really, then we are indicating this plus, then this would be omega cross r. Yeah. So this is the change of the. Another easier way to say this is the r dt is the elongation of this dt like this plus what I wrote in there, r times d theta dt. Okay, these are vectors. Okay, r times d theta dt. But it happens that, yeah, r theta dot or I theta dot, if you want to write it in another way also, this is plus r theta dot like this. The conclusion is that if you express this in vector form and in the cross product form, this is the best way, right there. Okay, so keeping in mind that this vector is this way and that one is like that. So we need to do a velocity diagram in here for this. We will do it graphically and we're gonna do it analytically as well. So and here, let's say this is the velocity input. It's actually like the other kind of Cartesian coordinates. So and here we'll go and do this. So this would be the velocities, okay? Velocities. So the velocity here, you have that this is r dot, and you have that this is omega cross r. In reality, the vector, the velocity vector, is the position derivative, and that is going to be the sum of these two. Like that. Okay. So if this is the case, hold on for a second. I'm gonna do this. Bring it back. Okay. So that's the velocity diagram. Or you could write it in a different way also. If we want to do this. If we want to write it, you could just write the component one is this way, r dot, and the other one is like this. And you could say, look, I am going to be attaching a rotating frame to it. This is the vector e sub r direction, and this is going to be the e sub theta. Okay? So where this is omega cross r. So what I was saying is that the velocity of the particle in the end, the velocity of the particle, vector velocity, is r dot vector plus omega cross r. Okay? Now, you keep in mind that the derivative of a vector always is the change in the length of the vector and the change in the due to the rotation of the vector. This is for the length, this is due to the rotation. Let's write the equation again, and I'd say, okay, remember, I will say remember that the derivative of a vector, dr dt, is the change in the length of the vector plus the change of the rotation. Okay, so you don't forget, we can write it down in here. Derivative of a vector always is change in length and the change in direction. Okay, now this is the velocity definition, the velocity. So don't forget this. For the acceleration, we have two choices. So the question is, what is this for the acceleration? The accelerate, let's just put here acceleration. This would have to be, that is the ddt of the velocity, which would be the r dt. Yeah. So we need to differentiate this vector. So why don't we just say that if the derivative of this would be to calculate the acceleration, we need to differentiate both vectors. Okay, I would like to see that we do this both ways, in a graphical form, and we do it in an analytical form. We could just derive this expression, that would be the analytical form, or we could just draw the derivatives of each one of the components, and then we do it graphically. I would like to take that approach first. So I'll just remind you what we have in here. Maybe it might not be a bad idea to repeat that over here, as long as I have my diagram in here. How many? Yeah, like this. And we had two vectors, right? we had this vector that is due to the change. This is your r dot vector. And then you have the other vector which uses omega cross r. And we said that we are going to propose a coordinate system where this is E sub r and this is E sub theta. Okay? And this was omega cross r. Okay. So you could say differentiate graphically first. All right. So if you look at the change of the vector here, let me just put the coordinate framing here. Yeah. So in here, what would be the change of length of the vector this way? It wouldn't be r double dot, right? Like this. But remember one thing, omega is rotating like this. Right? So the entire thing is rotating like this. So this would be as if we attach a frame to the rod and we describe on it the velocity and acceleration. So the first thing would be the elongation of this vector here. The elongation of this vector would be r double dot. The rotation would be omega cross r dot. And omega counterclockwise cross r dot would be perpendicular. Omega cross r dot. Yeah? So far, so good. But what about um, the other component? The other component is this one. So because it is a, we need to differentiate, like we need to take the omega cross r dt and understand this well. Okay, omega is a function of time and so is r. When you differentiate, remember the law of products. So we are going to have, first of all, the elongation of the vector would be omega cross r, which would be omega dot cross r plus omega cross r dot. Omega dot cross r plus omega cross r dot. See, these are the two. And then we need to do a cross product. See, omega is out of the board. Cross it with omega cross r. You're going to get this. Omega cross r. If you put your you're going to differentiate omega, which is out of the paper, out of the board, cross into omega cross r dot. So that's what you see in here. If we were to simplify this, these components, and then you'll have, let's say over here, you will have, the first one is the r double dot term. So this is this one, r double dot. Then we have the omega cross r, omega cross. See how it is? There's one in here and there's another one in here. So we'll add, this is omega dot cross r, and then the other term in here is going to be 2 omega cross r dot, and this one is going to be omega cross r. So if this is the case, we can conclude this. Therefore, you can conclude that the acceleration is equal to r double dot vectors plus we have this, no, okay. This would be omega dot cross r plus 2 omega cross r dot plus omega cross r. Let's give some names to these components of the acceleration. One is that this is called the relative acceleration. This is omega dot cross r. This is called the tangential acceleration. This one is called, to omega cross r is called the Coriolis acceleration. So that's, and then you have plus omega cross r. So this would be the Coriolis acceleration, and this would be the normal acceleration. Okay. If we write in terms of the coordinates r and theta, you end up with, you would say, in terms of coordinates, yeah, in terms of the coordinates, you could say that the acceleration is r double dot minus, now we have to put this with the omega squared times r in the what direction? In the e sub r direction, plus the other one would be in the, this would be omega dot cross r times 2 omega cross r dot. So, and this would be in the e sub theta direction. So this is another way of expressing the acceleration, or the total acceleration. So like I said, this is worst case scenario where we have all the components of the acceleration. And we have derived this using the graphs. And we could, like I mentioned, we could find the same expression. Wait a second, what did I write in here? This is a plus sign, not a parenthesis sign. And also at this point we don't use the cross product anymore. Omega dot, no, sorry, just, so this would be omega dot times r, and this is times r, plus 2 omega cross 2 omega r dot. We have the tendency to put the cross because we always operate with product, with vectors, but 2 omega times r. Okay, so these are the equations of motion for the, I mean, these are the equations of the acceleration and the velocity for any particle moving under plane motion.